Started recording.
Sharing the screen. Hope my screen is visible now to all of you. Yeah. So this is about the measurement error, measurement system analysis. So we'll try to understand bias, linearity, stability, and then in the afternoon, I'll take you through repeatability and reproducibility along with an exercise in gauge RMM, a live exercise of data collection and calculation of the error involved in the data collection. So every time you collect data, why are you collecting data? You want to study the variation, because yesterday you learned that variation is the source of defect, right? Variation is the root cause of defect. And variation can be of two types. One is process variation, another one is measurement variation. So what is process variation? Your process is failed to produce the output consistently around the target, and that is called process variation. But sometimes what happens when you actually study the capability of the process, when you collect the data, since your procedures are wrong, since people do not know how to collect the data, there could be variations due to the measurement system. So those variations are called measurement variation. It is nothing but measurement error. Your problem is process variation. This is not your problem. This is actually measurement error. So if you wanted to understand about the problem, you must first control the measurement error. Then only you can understand better, right? So the Six Sigma methodology aims to reduce the process variation. Before that, measurement system analysis helps in reducing the measurement error. You control and reduce the measurement error, and so that you can better understand the problem. So doing a project in an organization and trying to produce result is like driving a car in a highway. You need to reach the destination on time. First of all, you must reach the destination. Another thing is you must reach the destination on time. When you really wanted to do both, reach the destination as well as reach on time, it is very important you see the road while driving. Hope all of you agree with me. When you drive, you must keep an eye on the road and then continue driving. If you say, no, sir, I don't see the road, but still I will drive. Drive. Will you reach the destination? No. Will you reach on time?
No.
No. Right? Same way, when you say you will solve the problem, your eye should be on the problem. You must keep an eye on the problem. You must continuously see the problem and then solve it. But how do you see the problem? Through the data only you see the problem. So your data should be clean, your data should be credible, and so that the same data will make you understand the problem correctly. You can't solve a problem without understanding it clearly, right? So you have to be sure. During driving, if it rains, what will happen? Your windshield will be full of water. What do? You immediately switch on the wiper. Why do you switch on the wiper? You want to clean the water, isn't it, on the windshield? Same way, when the error is pouring in your data, you must do measurement system analysis, which will wipe out the error and then will allow you to see the problem correctly. MSA ensures the team focus accurately on the process variation and ensure the improvement efforts are used efficiently to reduce the process variation. So after MSA, you can see better and understand the process conditions better. Now, variation can be of two types: process variation, measurement variation. What is process variation otherwise called? This is the problem you want to solve. What is measurement variation? It is nothing but error. If you want to control this, first you must control this. And now measurement error can be of two types. One is accuracy, another one is precision. Accuracy means closeness to the true value. Accuracy means closeness to the true value. Precision means consistency. Accuracy means closeness to the true value. Precision means consistency. For example, the time consumed by a process, you call it cycle time. Let us say it is 100 seconds. Time consumed by a process is 100 seconds. You are given a stopwatch to measure the time consumed by the process. You measure it and then you record it as exactly 100 seconds. Are you now accurate? The cycle time of a process is 100 seconds. You have measured and you are also recording and noting down the time consumed as exactly 100 seconds. Now tell me, are you accurate now?
Yes, sir.
You are accurate.
Yes.
Why do you say you are accurate? The true value is 100, which is known to you, and the observed value is also 100. When there is no difference between true value and the measured value, you are accurate. I want you to measure it 3 times. All 3 times your reading is same 100. Now, are you consistent now? Are you
Yes.
You are consistent. You are accurate. You are also consistent. Is it both are required to make your reading speak the reality better? Both
Yes,
are
sir.
required.
Both are required.
Both are required. You need to be accurate. You need to be precise. You need to be close to the true value and you need to be consistent. And now why accuracy? Accuracy, no, you may become inaccurate if a difference exists between the true value and the observed value. The difference that exists between the true value and the observed value is called bias. So what is bias? The difference between true value and observed value. Let me repeat the same scenario. True value is 100. I want you to measure. You are measuring and saying me that it is 107. What is the true value? 100. But how much you have, how you measured and then recorded? You recorded it as 107. Are you accurate now?
No.
Because you have got a bias. How much is the bias?
7.
107. Yeah, 107 minus 100. 7 is the bias. As the bias increases, you proportionately become inaccurate. If the bias is 0, then you are fully accurate.
Accurate.
All of you understand bias? Yes.
Yes.
Bias measured over time. Over time, if the bias remains constant, that is called stability. If the bias remains constant, that is called stability. Bias remains constant over time. Whether you collect the data today, you collect the data tomorrow, you collect the data next month, or you collect the data in the next quarter, your bias is constant. Then your readings are stable. So for you to make your reading stable, you have to keep your measuring equipment, measurement system, in proper working condition. Am I correct? Then only you will get stable readings. Otherwise, what will happen? Over time, when you frequently use any gauge, what will happen to your reading? Your reading will slowly become inaccurate. Am I correct or not?
Yes, sir.
Yes.
So stability is important. Bias, the requirement is bias should be 0 and your reading should be stable. Not only that, if at all there is a bias, it should be linear. If at all there is a bias, it should be linear. For example, when we conduct the exam, let us assume we have a bias of plus or minus 5 mark. Let's say the exam is descriptive. That's why we are not going for descriptive. It's only objective. Suppose imagine the exam is descriptive. If a student writes an exam, our teachers evaluate and then they give marks with an accuracy of plus or minus 5. What does it mean? If you write an exam for 80, then result may be 80 plus or minus 5. You get my point? You write the exam for 80 marks. You have written it perfectly. You think it is 80. But anyway, final result is 80 plus or minus 5. You may get 85 also. You may get 75 also. Why is it happening? Because of the bias that you allow in your system. That is why objective type exam came. Am I correct? The measurement is improved. So sometimes what happened, I can conduct the exam. See, my bias is plus or minus 5. bias is plus or minus 5 when the examination is conducted for 100 mark. Suppose when I conduct the exam for 50 mark, I conduct the exam for 10 mark, I can conduct the exam for 1000 mark also. Now I have a measurement system which I am going to use for a different range of measurement. First one is just 10 marks, then it is 50 marks, then it is 100 marks, then it is 500 marks, then it is 1000 marks. Now you have got 5 different range of readings, and now I am going to use a measurement system. Now, if your measurement system's bias is constant across the entire range of readings, then your readings are considered to be linear. Suppose if the bias is not constant over the range, that is considered as a linearity issue. We'll discuss that, the graph. And coming on to the other side, precision, consistency. There are 2 possibilities. When 100 mm is the true value, when I am measuring the 100 mm, let us say I measure it 3 times. First time I say 102. Second times I say it is 104. Third time I say 106. One appraiser measured the same product, measured the same characteristics multiple times. But he gave different reading. He is not supposed to actually. You are measuring 100 mm, all 3 times you should have given 100 mm. Right? But no, you gave 102 in the first time, 104 in the second time, 106 in the third time. One thing is, you are not accurate. Keep it aside, one side. But when I look at your reading, 102, 104 and 106, how can you give me 3 different reading measuring the same product 3 times? This error is called repeatability error. Do you all understand what is repeatability? The error within the readings of single appraiser is called repeatability error. The variation you observed within the readings of a single appraiser is called repeatability error. All of you understand what is repeatability error? Yes or no?
Yes.
Yes, sir.
Another thing
Sir,
is
can you repeat the statement?
single appraiser is asked to measure multiple times, but the product is same. Measuring gauge is same. Operational definition is same. Measuring person also same, but the reading is different. Can it be considered an error? That is repeatability error.
Okay.
Clear? Now imagine there are 2 people involved in the measurement. I measure and then my reading is 105. Same product, now you are asked to measure using the same gauge. Now you are saying 110. I am saying 105 and you are saying 110. But we both are measuring the same product. We both use the same measurement system. We are in the same project. But we disagree between each other. The disagreement between the appraiser is called reproducibility. Right? The difference or the variation bit in the readings between the appraisers is called reproducibility, and the variation observed within an appraiser is called repeatability. Hope you all understand, right? So you must control repeatability also. You must control reproducibility also. Then your readings becomes consistent. If your readings becomes consistent, when you calibrate the equipment, your equipment will start giving accurate reading. If your readings are not consistent, then calibration will be a big challenge for you. If your readings are not consistent, calibration will be a big problem for you. Am I correct?
Yes.
First situation. This is the true value. The purple color dots are the measured value. The measured values are close to the true value. Yes or no?
Yes.
Yes.
So your readings are accurate. All the purple color dot, are they close to each other?
Yes.
So your readings are not only accurate, it is also precise.
Yes.
Coming to the second scenario. Your see here, your true is here. There are multiple readings here, multiple purple color readings. When there are multiple reading, in order to measure the accuracy, what we generally do is we take average of all the values. We take average of all the values. For example, this is 100. This point is 105. This point is 95. When you have 2 points, 95 and 105, calculate the average. What is the average of 95 and 105? Come on. 95 and 105. What is the average? 100. When
100.
you take the average, you automatically come to the true value. So when your points are symmetrical, around the target, see here it is distributed like this. You take the average, your readings can still be accurate. You all understand what I am telling now? Average is one of the statistics. How do you get the average? You add all the number, divide by the number of items. That is average. By calculating average, you can make your readings accurate. This is the main reason. Always we collect data, we collect data in multiple samples and then use the average for our conclusion, because average will help us, to go close to the real value by minimizing the error in our reading. Right? Understood. So the readings are accurate, but since the readings are scattered, not close to each other, I will consider this as not precise. Accurate, but not precise. But coming to the third situation, true value is here. All your data points are here. Even when I calculate the average, my average is here only. Am I accurate now?
No.
I am not accurate. But am I precise now?
Yes.
Yes.
I am precise but not accurate. And final situation. True value is here. My observed values are here. When I take the average, average comes here. Am I accurate?
No.
And am I consistent? Am I precise?
Less precise.
No. Right? And see here the points are scattered away. So not precise. Now you understood the difference between accuracy and precision. Please note the requirement is you have to be precise and then you have to be accurate. You have to be precise and then you have to be accurate. And these terminologies I have already taught you. Bias. So what is bias? The difference between the average of the measured value and the true value. Do you all understand the meaning of bias?
Yes.
The average of the measured value and the true value. Means bias over a longer period. Your project is running for 6 months. Throughout the 6 months, you are going to collect the data. So it is very important. Your reading should be stable. It is very important you maintain the measurement system under similar conditions so that your readings can be stable. Otherwise, what will happen? First month, your readings will be accurate. Second month, your readings will be inaccurate. And again, third month, it will be still worst. So this can happen. Do not allow the bias to keep on increasing or decreasing. Try to maintain it at a constant value. The advantage is when you maintain it at a constant value, you can calibrate and then easily arrive on the true value. For example, my watch always goes 10 minutes past. I am checking the time. It is showing 1 o'clock. But what is the true time now? 12:50. Because my watch has got a bias of how much? 10 minutes. Every time I want the true time, I will check up my watch and subtract 10 minutes. Immediately I will get the true value. This is why we expect the bias to be constant. If the bias is constant over time, your measurement system is considered to be stable. Your data is considered to be stable. Linearity, bias over range. What is range? Imagine you measure a characteristics. Let us say you are measuring current. You measure current from 5 ampere till 100 ampere. 5 ampere, such a small current, and 100 ampere on the other side. And now, when you use the measuring equipment, maybe an ammeter you use, and see to that the bias is maintained constant throughout the range, throughout the working range. If you are not able to maintain the bias constant throughout the working range, then break the range, and then different gauges, and then use different gauges. For example, 5 to 100, I will break it into 5 to 25, then 25 to 50, 50 to 75, 75 to 100. Then 5 to 50, I use a gauge. 50 to 75, I use another gauge. 75 to 100, I use another gauge. You know why? Then only calibration will become possible for me. If the gauge is going to give me different bias, I will not know what to do. It is something like wearing a watch, which can give time, in a, what do you say, in an unstable manner. For example, in the morning, it runs 10 minutes faster. After 2 hours, it runs 15 minutes slower. Again, after half an hour, it runs 40 minutes faster. Will you be able to find out the true time using your watch? The behavior is erratic. So it's very important. Your bias is maintained constant in the working range. You are going to use a gauge from 5 ampere to 50 ampere. At least in that range, the bias should be constant. And so if you are able to maintain that bias as constant in the measuring range, then you are linear. Otherwise, the problem is, you can't calibrate your gauge and then your readings can never be accurate. So all the bias stability, linearity, and bias are components of accuracy. If the bias is 0, if your readings are stable, if your readings are linear, then your readings can be accurate. Resolution is nothing but the least count. Hope all of you know least count. Am I right? Least count is understood? You know, right? We'll discuss the minimum reading that you can get from your gauge. That is called least count. And repeatability, reproducibility, I already explained. The variation within the same appraiser is repeatability. The variation between the appraiser is reproducibility. And now the discussion is only limited to bias. See here, there is an example. You have a standard workpiece. Standard workpiece, the dimension is 25.4 mm. 25.4 mm. And you are asked to measure it 10 times. And you also measured it. And you gave me readings like this. Do you notice a variation in your reading? Do you notice a variation in your reading? First time 25.425. Second is also 425. Third is 400. And fifth, then someone is other one is 0.375. There is variation.
There is.
Is this way? Your doubt is this variation is due to the process or to the measurement? Can somebody now tell me the variation what you are seeing here in the data, is it due to the process or due to the measurement?
It's a measurement error.
Very good. It is measurement error. How are you sure? How are you surely telling it is measurement error?
Since we are using the one master, it is approved by the someone.
Very
Lab
good.
or
Since you are using the standard workpiece, different readings are not possible, isn't it? Same part has been measured 10 times, but readings are coming different. That means the possibility is only measured. So now in order to quantify the measurement error, you are going to calculate the bias. How to calculate bias? True value is how much? 25.4.
25.4.
The difference between true value and the observed value is called the bias. But observed value, 10 values are there. Then how will you calculate the observed value? Can you find out the average of it? Possible? Add all the 10. Add all the 10. Divide by 10. So how much you are getting? The observed value is 25.4051. Average of the observed value is 25.4051. 25.4051, the observed value minus true value 25.4. What is the difference? 0.0051. 0.0051 is the bias. All of you understand how to calculate bias? Yes?
Yes.
If your observed value is more than the true value, your bias will be positive. If the observed value is lower than the true value, your bias will be negative. When your bias is positive, in order to get the true value, in order to do the calibration, the observed value should be subtracted by the bias. Correct? When I subtract, the observed value is 25.4051. When I subtract the 0.0051, can I get the true value? Come on.
Sir,
Sir, could you repeat that?
Observed value is 25.4051.
Okay.
Okay.
From this, I subtract the bias value. Bias is 0.0051. Now,
Okay.
result will be 25.400. Am I correct?
No.
Yes.
How?
You subtract and tell me 25.4051 minus 0.0051. How much
Yes,
it is?
sir.
True value will come.
25.4.
Yeah.
That means from the observed value, you can get the true value by subtracting the bias.
Yes.
There is called
Right.
calibration. This procedure is called what? Calibration, right? So
Yes.
your equipment will be calibrated only by understanding the bias in your reading. So that after calibration, when you use the equipment, your reading will be bias free. And bias can be expressed as a percentage of the tolerance. In this particular gauge situation, tolerance is known. Tolerance is plus or minus 0.25. Tolerance is generally provided. So plus or minus 0.25 means the total range of tolerance is plus 0.25 minus 0.25. It is 0.5. The range of reading is 0.5. Considering the range, the bias is 0.0051. So it is understood. Bias is 1.02% of the tolerance. So bias expressed as the percentage of the tolerance of your maybe measuring gauge or whatever tolerance as a percentage it is expressed, right? Understood, all of you?
Yes.
Now, I already told you linear. True value taken in the x-axis, measured value taken in the y-axis. Here it is 0, here it is 100. Here it is 0 ampere, here it is 100 ampere. For measuring current, current is varying from 0 ampere to 100 ampere in a particular circuit. Your people are measuring. When they measure 0, the observed value is 0. When they measure 100, the observed value is 100. Your readings are accurate. No, you see the black color line. The black color line means your readings are accurate. Why your readings are accurate? Bias is 0. Bias is 0. Are you able to maintain the accuracy throughout the range of the reading? Come on, tell me. From 0 to 100, are you accurate at all the points along the black color line? Yes or no?
Yes.
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 Then your readings are perfectly linear. If the bias is constant across the range of the reading, then you can say your readings are perfectly linear. We prefer such a scenario. Suppose, let us say the bias is not 0. Current is 0 ampere, but your ammeter is showing as 5 ampere. So your reading will come here. Am I right? 0 is recorded as 5 ampere. You know why? There is a bias of 5 ampere. Now tell me, for 1000, let us say, here it is 1000. For 1000, what will be the reading? Your reading? Bias is 5, isn't it? So,
1005.
value is 1000. What will be the recorded value?
1005.
Very good. So, instead of 1000, you will record it as 1005. So, at the lowest value also, the bias is 5. Highest value also, bias is 5.
5.
Now, after collecting the data, you can subtract 5 ampere from all the data at the black color line. Is it possible?
Possible, sir.
That
Yes.
means you can make your readings error-free if your reading is linear. Suppose if it is not happening in this manner, if the bias is not constant, you draw the line. See here, green color line. The green color line, when you go across the green color line, the bias keeps on changing. Here it is no bias. When I come here, there is a small bias. When I come here, some moderate bias. When I go to the maximum extreme, the bias is too much. Now action taking will be very difficult for you. Am I correct? Correcting error is difficult for you. So linearity is an unpreferred scenario. Linearity is unpreferred scenario. When your readings are coming like this, the choice of the gauge you have taken is not appropriate. Please try to break the range. When you want to go for 0 to 1000, there are divide it into 10 ranges, 0 to 100, 100 to 200, 200 to 300. Then for each range, you have an appropriate ammeter. Thereby, at least within the range, all your reading will be linear. Only when the readings are linear, only when the readings are stable, calibration is possible. Otherwise, you have to play the game of inky panky to arrive on the true value. All of you understand what I am talking now?
Yes, sir.
Very good. So all the three. So the solution to the problem is to make your readings accurate. The solution is calibration. If your readings are not stable, the solution is increase the frequency of calibration. Maintain your equipment frequently. Your equipment also deserves some maintenance, isn't it? You have a metrology lab where you keep your equipments like the dial gauge and other things. It is very important your gauges are maintained in a good condition to give you stable reading. Suppose during the project, if somebody drops your dial gauge, what will happen to your readings on the next day? The readings will become biased. Am I right? Yes or no? If somebody drops your gauge onto the floor, can you
Yes.
use this for the next day?
No.
It should be maintained, right? So whether you are, if you really wanted to understand whether your gauge is in proper condition or not, if the readings are stable, that's an indication that your gauge is maintained properly. If the readings are not stable, that is also an indication that you are poorly handling the equipment, you are not maintaining at appropriate frequency, and you are not calibrating in the appropriate frequency. Maybe you need to increase the frequency. It's not sufficient. You just calibrate the equipment once in a year, maybe once in 3 months you need to calibrate, and then some maintenance have to be done on every single day to make your reading stable. So you can monitor the stability of the gauges using this kind of graph. This graph is nothing but control chart. The control chart will bring any, if there is any issue related to stability, control chart will give a signal. Point to point, deviating from the average too much is a signal that your gauge has become unstable. And so some corrective action have to be taken to bring all the readings under control. So these things you need to do. So we understood stability, we understood linearity, we understood bias. The requirement is bias should be 0. Stability means your reading should be stable. That means bias is constant. And then linearity means it should be perfectly linear. If you plot the point and draw the graph, it should be a perfect straight line. It should be a perfect straight line. And if the perfect straight line is not coming, if the line is going inclined, you can understand there is a linearity. And solution to all the three, the accuracy related problem is calibration, 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 improve the frequency of calibration, and then maintain the equipment properly, and also choose the equipment appropriate to the range of the reading. These are all the solutions, right? So I stop here and I'm now open to your questions. And if there are no questions, we can continue the discussion post lunch. Any questions now? Recording may be stopped.